Welcome to this lecture. This would be lecture number 8 on chemical kinetics, and again as we do every time, quick recap of what we covered in lecture 7. So, we had started looking at these integrated rate equations, and before looking at an example of the same, we had introduced the concept of half life, and we had even said that this half life can be treated as a preliminary check of the type of reaction you have at hands, or the type of reaction you are studying, right. And then we moved on to the first example of a rate of an integrated rate equation, which was that for a zero order reaction. So, remember when what we did was for the zero order reaction, we took an equation like this, right. And in this equation what we did was we had this A going to P, right, and then we set up the rate equation as is seen here. So, the most important one being minus d of A over d of t is equal to k. Then we went ahead and integrated it. We ended up with something like this. Okay. We ended up with something like this, where when we are integrating between limits t is equal to 0, we have concentration of A, the reactant, to be its initial concentration A naught, and then at t is equal to certain time t, the concentration of A would be concentration of A at time t. So, we go ahead, do the same, and what we end up with is this characteristic rate equation for a zero order reaction. So, this is again the signature of a zero order reaction. What does this mean? What it means is that if you would plot the concentration of A at a given time, right, against time or versus time, you will be getting a straight line, because this is an equation of the type y is equal to mx plus c, and this equation the plot would be having a negative slope, because your slope in this case is minus k. So, this is what we plotted last time. As you can see, the intercept would be A naught and the slope is minus k, right. Again, if you would read what is written out here, only if the plot of concentration of A as a function of time is a straight line, then this is definitely a zero order reaction. From the plot, what can you do, or what can you get? You can get the intercept, which would give you the initial concentration A naught, and you can also get the slope. That means, from the slope you will get the rate constant, because slope is equal to minus k, and hence it will give you a positive value of the rate constant. Again, we ended the class with this expression for the half life of a zero order reaction. So, what we did was, as the half life was defined, T of half is that time at which the concentration, the initial concentration, falls to half of its value. So, if the initial concentration is A naught, the half of it would be half of A naught, right. We put it back in the equation, the rate equation for the zero order reaction, and this is what we ended up with. And the final expression for the half life was this, where T of half is equal to concentration of A naught over 2 k. So, what it means is that the half life is proportional to the concentration of the reactant, or the initial concentration of the reactant. In other words, what it means is that higher the concentration, higher is the half life. As the reaction proceeds, your concentration is decreasing, your half life is also decreasing, and this would be another signature of a zero order reaction, which then brings us to this feature of a half life, where we had said that the half life indeed can be used as a preliminary check of the type of reaction you have at hands. Okay. So, we stop there, and what today we will do is, we will start with what we commonly refer to as the first order reaction. Right. So, in the first order reaction, we would again take this reaction A going to P, okay, I will just check the number of the last equation I had used, so that I can start from there. Okay. The last equation number was 7, so I will start from there. Now for this, as it is being defined, the first order reaction, then I can write the rate is equal to K, the rate constant, times the concentration of A. Okay. So let this be 8. So in continuation from the 0 order reaction example. So if this is what it is, then from the equation or the reaction out here, what we can write is that minus d of A over d of t is equal to K times the concentration of A, right. So once you have set this up, then it is very straightforward. The key point is to set this expression or this equation up. Okay. Once you have this, then we go ahead and we write that minus d of A. So this is what we had, I am writing it again, is equal to K times concentration of A. So this was equation 9. So if you are having that, what we will now do is we will bring A on one side and take dt on the other side. So that is, we are going to have A over A is equal to K dt, right, and then we move forward and we integrate. So what we will do is we will integrate again between some well defined limits. We will take the negative sign on the other side, K, we can integrate it like this, again at t is equal to 0, again at t is equal to 0, the concentration out for A would be A naught, at t is equal to the t, the concentration of this would be T. Okay. Remember, this K is a constant, so it can be taken out of the integration, and hence we have this. So now we go ahead and integrate. So on the left hand side, you realize that this is your standard integral involving your natural log. So then what you get from here is, based on this, I write natural log At, where natural log is log base E, minus natural log A naught is equal to minus Kt, right. So this can be again written as natural log of At. So let this be 10 is equal to natural log of A naught minus Kt, 11, right. So the other way of writing this equation is that, again if I write it from here, I can write it as natural log A t over A naught is equal to minus Kt, right. So let this be 12, okay. And then what I can do is I can go ahead and write like this, A t over A naught is equal to e to the power minus K t, okay. Let this be 13, and finally what I can write is, so this e being meaning exponential minus Kt, that is the order of the exponent out here, and then I can write A t is equal to A naught e to the power minus Kt, or so another way of writing is A of t is equal to A naught exponential minus Kt, okay. So let this be 14. So this is your rate equation for a first order reaction. So please again let us go back and take a look at these. So we started with this, where minus d of A over d of t is equal to K times A, K being the rate constant. Then we rearranged, so that A came to one side, the T went to the other side. We integrated between the limits. What were the limits? At T is equal to 0, I would be having the concentration of A as concentration of A naught. At T is equal to T, the concentration of A is given as concentration of A T outside the large brackets. We integrated within these limits, right. The one on the left hand side is a logarithmic integral, a standard integral. The other on the right hand side is just k times t, okay, and hence what we get is an expression like this, right. So, natural log of A t minus natural log of A naught is equal to minus k t. If you rearrange this, chemically in this form, then from 10 I get 11, right. The other way of doing it is, instead of keeping it in the form of 11, I go ahead and express it in this form, where natural log A of t over A naught is equal to minus k t. What this tells us is that the expression can now be rewritten as concentration of A of t over concentration of A naught is equal to e to the power minus k t, from where I get this expression, where A of t is equal to A naught e to the power minus k t, or A of t is equal to A naught exponential minus k t. What does this mean? What it means is, if you focus on this equation, what it means is that equation 14, it says that concentration of A naught is what? Concentration of A naught is the initial concentration, T is the time that has elapsed since my reaction has started. What is K? K is the rate constant, okay, and you immediately realize that what the equation is trying to tell you is that the concentration of A at time t is what is essentially an exponentially decaying function. That means the concentration of A naught, what would happen? The concentration of A naught or the concentration of A from A naught would decay exponentially as a function of time, right. And what is the nature? It is always exponential, but what is the rate? So, rate is given by the rate constant. So, k t, what it is telling you is that this exponential function would decay. A naught, you start from A naught, it would decay like this, right, exponential, and the decay constant which we will come back to later. So, just hold on to the thoughts, this concept, this decay constant is your rate constant, which is k, right. Okay. Now, what can we do with this? You have seen different variations of the same equation. Now, let us take these variations one by one. So, for example, let us go back to this variation, which was the one we said was equation number 11. So, from equation number 11, if you write this one down again, right. So, let us write this one down. Remember, we are still talking about a first order reaction, A naught minus k t. So, this was our equation number 11. So, what this again immediately appeals to you is that, oh, this is the equation of a straight line, right. So, this is the equation of a straight line, which means if I have a plot like this, right, if I have the natural log of my concentration out here, if I have the time on this axis, the x axis, and if I plot it now, I will be getting a plot which will look something like this, a straight line, right. And from the straight line, what are you going to get? So, one is I get the intercept. What is the intercept? The intercept is this, and from the slope, this is equal to minus k, right. So, the slope is negative, this is equal to minus k, and hence from the slope we get the value of the rate constant, which is k. So, this is the rate constant. How you get the rate constant for a first order reaction if you plot it like this, okay. So, the other way of saying this is the signature of a first order reaction is what? The signature of first order reaction then can be written like this, that if I can write this as, if the experimental data fit first order kinetics if the experimental data fit first order kinetics, then the plot of ln A t against time will be a straight line, as we saw, that is linear with a negative slope obviously, and from the slope what you would get is the rate constant. Slope is equal to minus k, again slope itself being negative, the negative signs cancel out and then you get the value of the rate constant. So, please remember that this is important, that the plot of this quantity, right, log base e of A versus time or against time has to be a linear plot with a negative slope for the reactant. This was one way of looking at it, or at least you also understand that if you are encountered with a plot which has this characteristic, then immediately you can pin it down and say that yes, this is a reaction which follows first order kinetics. Great. Now, let us talk about half life like we did for the zero order reaction. So, let us talk about this. So, when when we do this half life, remember what was half life? We said the half life which is denoted by T half is what, where the initial concentration A goes down to half of A naught, right. So, that means you start with initial concentration A naught and the time it takes to go down to exact half of the concentration is your T half. Now, what is the expression for T half, right? We can again get it multiple ways. So, suppose I do it from this equation where I knew that natural log A t over A naught is equal to minus k t, and if you would remember this was we had written before equation number 12. So, again I will write this was equation number 12. Now, suppose I have T half, then when I am saying T half, then I can write natural log A, this would be, sorry, let me write on the next page. So, when I am saying T half, remember I am considering half life, I am saying at T half, right, then this is natural log the concentration of A at what time, at time t is equal to T half over A naught is equal to minus k t, where t is T half, right. Okay. Now, by definition T half is what, that point or that time where the concentration of A naught has become half of it or half A naught. So, then I can write natural log half A naught over A naught is equal to minus k T half, is not it. So, obviously then you realize this A naught cancels out. If this A naught cancels out, I will be having half is equal to minus k T half, right. So, let me see what was the last equation number. So, I can put the equation number in, that was 12, I think it was 14. So, let this equation number be 15. So, let this be 16. Okay, from here what would I get? So, what I get was from here what I get is I can immediately write that, hopefully you will realize from here I can make this transformation to go to T half is equal to what? I am sure you realize is 2 over k, right, and this can also be written as what? T half is equal to 0.693 over k. So, this is 17, 18. So, this was the working equation for calculating T half. So, even if you forget, that means there is no need to memorize, as long as you understand the steps that are being taken to calculate T half. That is the point I am trying to make out here. Then once I do this, the natural log of half is equal to minus k T half, right, and from here I am sure you will realize that what I get is the T of half is equal to log base E2 over k, or T of half is equal to 0.693 by k. So, now what you have done is you have got an expression for T half for a first order reaction, right. You have got an expression for T half for a first order reaction. How is this different from that of a zero order reaction? You see, in this expression for T half there is no concentration term, there is no concentration term. So, this T half is a constant, is equal to 0.693 is a constant over k, which is a rate constant, which is constant for a given reaction, right. So, which means is that we can write the half life, we can write that the half life for a first order reaction, the half life for a first order reaction is independent of the concentration of the reactant. Okay. So, again the half life for a first order reaction is independent, this is the key word, the half life for a first order reaction is independent of the concentration of the reactant, that is it takes the same value, this T half takes the same value no matter what the extent of reaction is. So, again I write, that means T half takes the same value no matter what the extent of reaction is, right. So, T half takes the same value no matter what the extent of the reaction is. So, it is immaterial at what point of the reaction you are, you try to get T half, say from initial to half of it, or from T half to half of that, which is T 1/4, like we were doing T of 1, T of 2, T of 3, or to go to 1/8 of A naught, right, which is third T half life. All of these T halves have exactly the same value. Why? Because based on what you have derived, it has no dependence on the concentration, that is, it does not show any dependence on the concentration of the reactant, rather it is a constant which is given by 0.693 by k. Again 0.693 is a constant, k being of that reaction is always a constant. So, T half is a constant. So, again if you would remember that when we were discussing T half, even before we had started with the zero order reaction, I had shown you a plot, I will show the plot to you again, where I told you that the fact that these T halves are equal might be a signature or is a signature of a first order reaction, and that is what you have shown right now by doing a quick derivation starting from your integrated rate equation. Okay. So, this is the power of T half, right, again it is a preliminary check. So, if your T half is constant throughout, it tells you that it is a reaction following first order kinetics. Great. Now, let us look at something a little bit different. or before that let us take a small example. Now, when I take this example, just be careful of what we are discussing right now, because it is a first order reaction, but with a slight difference. So, what I mean is, for example, take this following decomposition reaction. So, 2 N2O5 going to 4 NO2 gas plus O2 gas. Okay. So, this is the reaction I am following. So, when I am following this reaction, I am told that this reaction also follows first order kinetics, that means rate is equal to K times N2O5. So, the decomposition of N2O5 is following a first order kinetics, right. Now, think about the derivation of the rate equation, the integrated rate equation based on this. Now, when I write, so you do exactly the same thing, you know that rate is equal to K times N2O5. Now, also the rate of the reaction from the stoichiometry is given as minus 1 by 2, that nu of the reactant, nu being the stoichiometric coefficient, times d of O5 over d of t. Let me write again, is equal to minus half, right, d N2O5 over d of t. Okay. So, this is my expression for the rate, okay, in terms of the disappearance of N2O5. Now, if I try to derive, that means if I try to get the integrated rate equation for this, this is what I will do, right. What I will do is I will equate this one and this one, right, I will equate this one and I will equate this one as we did before. So, when I do that, see, there is a difference coming in. The difference is like this, I write now minus half d of N2O5 over d of t is equal to what, K N2O5. So, this is my equation right now, let this be equation number 19. Now, again I go and do exactly the same thing, but then a small difference creeps in, if you would keep track of what I am doing. So, what I do now is I say that, okay, this is d N2O5 over 2O5, but I have a 2 out here, is not it. So, I will write it as minus 2 K d of t. Once I write it as minus 2 K d of t, then what I do is I integrate. What do I integrate? I integrate again between the limits. What were the limits? So, the limits are N2O5, the initial concentration at t is equal to 0, then this is N2O5 at time t, this is at time t. Okay. Again exactly the same thing as we did last time, just keep track of this fact that here K is a constant, so is 2, so this 2 K can be taken out of the integral sign, and then what we go ahead and write is that, okay, so I will write straight away natural log N2O5 t minus natural log N2O5 0 is equal to minus 2 K t or ln N2O5 t is equal to ln N2O5 0 minus 2 K t, right. Now, what is the thing that I am trying to drive at? So, let this be equation 20. Compare this equation with the equation we had derived before, which was equation number 11. See, this is equation number 11 that I had before, where, so if I move it here, this is the equation number 11 if you read at the bottom of your slide. So, ln A t is equal to ln A naught minus K t. Now, this reactant has become N2O5, right, at time t is equal to ln N2O5 naught initial concentration minus 2 kT. The difference you see out here is that here I have a 2 K, here I have a K, right. As such everything remains the same, the only problem being here I had that stoichiometry out here for N2O5. When I derived it I said A going to P, here I am saying it is 2A going to your products, right. So, hence that stoichiometry has to be taken into consideration, and how do I take that into consideration is, well, first of all I had done this derivation, I know that this 2 is coming in to the picture. So, now what I will do is only I keep track of this, and then if I would be having a plot of time, and this is N2O5, if I would be having a plot of this, right, when I plot this you see what I will get is something like this again, a straight line, right, sorry this is straight line. So, what would my intercept be? My intercept again would be natural log N2O5, that is the initial concentration, but look at the slope, look at the slope now, the slope is equal to minus 2 K, the slope is equal to minus 2 K, this is what is important. So, that stoichiometry which appeared in that equation, right, the stoichiometry which appeared in that equation here where 2 N2O5 goes to 4 NO2 plus O2, this stoichiometry it has to appear, right, it has to appear, stoichiometry is important. So, where did it appear? So, it appeared when you were trying to calculate the slope, then if slope is equal to minus 2 K, then you write then K is equal to slope over minus 2, right. So, this is how the reaction stoichiometry is taken care of, right. I hope I have been able to put this point across, that when you have the stoichiometry coefficient, you say nu j or whatever is equal to 1, it does not matter, right, because the slope is equal to K, but the moment it is different from that, the moment it is different from that, this is what comes in. Thus I can I can generalize it, right, so that it is easy for you to remember or easy for you to apply. So, to generalize what I can write is, if for any reaction I have, so to generalize, if for any reaction, right, I have say 2A going to products, or this was for N2O5, I can say A going to products, where A is the stoichiometric coefficient, right. So, the moment I have that, then I write that the rate is equal to minus 1 by A d of A over d of t, right. This is equal to K times concentration of A being a first order reaction, and when I go ahead and do the integration, what I end up with is that natural log of A, right, t is equal to natural log A naught minus A K T. This is extremely important, and I would give this 21. So, here is an extremely general form of your integrated rate equation in the linear form for a reaction following first order kinetics, where A is the stoichiometric coefficient in front of the reactant. If A is equal to 1, it falls back to equation 11. If A is not equal to 1, then just use this. Great. Yeah, as I was telling you, there is one more important thing that we talk about often when we consider a first order reaction. That important thing, though it's a little bit beyond your syllabus right now, but I think because we are talking about first order kinetics, it's highly important that you keep this in mind, right. What we say is something referred to as a relaxation time. Okay. Now, do not worry about it, it is actually very simple. The relaxation time is given this symbol tau, right. So, this symbol is tau. Okay. Now, what do I mean by the relaxation time? So, suppose I have an initial concentration for a first order reaction, the initial concentration A naught, right. I am still sticking to the reaction A going to P, right. So, A naught, then A naught at a certain point of time, the A naught concentration is decreasing from A naught, and I get a value of A naught which is like this. What is it? So, at a certain time t, this A naught is equal to 1 by E times concentration of A naught. Okay. Now, this 1 by E concentration of A naught is important. Why? So, 1 by E essentially is the inverse of your E, right, but what it tells you is that the time it takes for A naught to go there to 1 by E of its original value is referred to as the relaxation time, right, which can be symbolized as tau. So, again what is the relaxation time? So, the relaxation time is nothing but for A naught to decrease to that concentration which is 1 by E of its original value. So, what was T half? T half was that concentration or that time it takes to decrease to half of its original value, that is half A naught. So, relaxation time is that time it takes to reach a concentration which is 1 by E of its original value, and if you remember what the value of E is, then 1 by E is nothing but can be written as A naught is equal to this 1 by E, right, when we say A naught is equal to 0.368 A naught. Okay. I would say this is at time t is equal to tau. So, when A is at time t is equal to 2 is equal to 0.368 A naught. Okay. So, what has happened? What has happened is that at time t is equal to tau. So, let me write again, at time t is equal to tau, the concentration of A is 0.368 A naught. Okay. So, what it means is that after this time tau has elapsed, it has decreased to 0.368 A naught. That means what I can write is, just follow this, what I am writing is that at t is equal to tau, which is the relaxation time, at t is equal to tau, which is the relaxation time, the reaction has gone to 63.2% completion, 63.2% completion, until and still has how much to go? 36.8% to go, right. So, again what is this relaxation time? This relaxation time is that time where the concentration of A at t is equal to tau has decreased to 0.368 of A naught, and in words it means that the reaction has gone to 63.2% completion and still has 36.8% to go. So, that is the definition of a relaxation time. Okay. Like we found an expression for T half, we can also find an expression for this relaxation time. It is very easy. What we do is we recall this equation where we had concentration of A at time t is equal to concentration of A naught e to the power minus k t, right. This was equation number 14 for us, if I remember correctly. Now, what we are saying is at t is equal to tau, right, the relaxation time, this A of t is what? So, at t is equal to tau, this one is 1 by E A naught. So, 1 by E A naught is equal to A naught e to the power minus k t, right, or I can write 1 by E is equal to e to the power minus k t by cancelling A naught from both sides, or I can write e to the power minus 1 is equal to e to the power minus k t. So, this is, remember, this is t is equal to tau. So, now I can write e to the power minus 1 is equal to e to the power minus k times tau, where I have replaced t by tau because tau is the relaxation time. Now, then once I have this, so if this is say 15 for me, then I can easily write this one as e to the power 1 is equal to e to the power k tau, right, or I take natural log on both sides, or I can write straight from there, so it does not matter, this is equal to k tau, right. Hence, this is 1 on this side, so I can write k tau is equal to 1, or what is tau? Tau is equal to 1 by k, right, or tau is equal to 1 by k. So, this is an expression for the relaxation time, and let this be, I forget, oh sorry. So, I missed out the equation number, just hold on, let me see what the equation number this one would be. Okay. So, I guess this one would be having equation, just let me check one thing. So, I have generalized, okay. So, this one would be having equation number of 22. So, please change this one would be equation number 22, and I can say this one is 23. So, the way the relaxation time was defined, it was defined that it comes down to 1 by E of its value, right. So, 1 by E of A naught. So, once I know that this relaxation time corresponds to that concentration, which is 1 by E A naught, I put it back in my integrated rate equation, trying to find an expression for tau, which is the relaxation time. I go ahead, do it, and then I end up with a very simple expression for tau, which is equal to 1 by k. That means, what is tau? See, tau is units of time, whether it is minutes, seconds, hours and so on. Remember k, what is k? For a first order reaction, k has the units of inverse of time, and it makes sense that tau is equal to 1 by k even in terms of units, right. So, the inverse of k would be your units of time. The only thing you have to keep in mind, when you are talking about relaxation time, this is the only thing you need to know relaxation time. It becomes handy in many cases. Well, as I was telling you, the only important point is that this relaxation time is only applicable. So, tau or relaxation times are only applicable for first order or pseudo first order reactions. Okay. So, sorry, relaxation. So, reaction times are only applicable for first order or pseudo first order reactions. This is something you would like to keep in mind. I will end this section on first order reactions by this plot, so that you can have a better feeling of what we have discussed up till now. So, the plot goes like this. Let us see whether I can draw it properly. Okay. So, here what I am having is, I am having, well, let us say this I mentioned, this is my time, okay. This is my time, this is my concentration of reaction on y axis. What I say is, this is my 100%, okay, 100% means I have, so this is 0 time, so I have 100% of the reactant, no product, this is my initial value A naught, so which I say is 100%, right. Now, if you remember that one of the expressions, okay, so one of the expressions for let me bring this one back, yeah, one of the expressions for a first order reaction was this, that the concentration of A, how does it change as a function of time? It changes as e to the minus k T, and when T is equal to 0, the concentration is A naught, right. So, that is what we are doing here. So, at T is equal to 0, the concentration is A naught, which is 100%. So, I am saying that is 100, so it is normalized to 100% because that is the maximum I can have. So, that is 100%, right. Now, it is going to decay exponentially. So, let me try to draw exponential decaying function. Now, let us see, can we do something else with the graph based on the discussions we have had until now. So, what is T half? T half is that part where this one would decrease to say 50%. So, this is 50%. So, this is I say this is percent, right. So, that is okay. So, sorry, this is yeah, this is percent, right. So, percent of reactant remaining. So, when I say 50%, it is not exactly drawn to scale, then what is this? So, this is my T half, this is my T half, right. Now, remember the relaxation time, what did the relaxation time say? The relaxation time said that I would decrease here, I would decrease to what value? I would decrease to about 63% of my initial value, that means the reaction is gone to the extent of 63.2%. So, if I do that, if I say that this is about that 63%, right, then I can say that from here if this is say 63.2% to roughly, okay, then this tau or this T on this axis would be referred to as what? Would be referred to as tau. So, if I go from, well, let me do it here, it is easy for me, from here to here, this would be tau, okay. So, this would be tau. So, this is my relaxation time. So, you realize that even after this time is significant, now there is about the rest of the reaction 36.8% of the reaction has to go on, okay. It is not exactly drawn to scale, but hopefully you understand the point I am trying to make is that from this graph we can figure out what the relaxation time would be if I am given a plot like this, right. Now, what about the other T halves? So, see, so from 50% 0 I come down to say another half somewhere here, right. So, that would be 25 for me. So, if I do 25 and again if I try to make some sense, so this would be the other T half for me. So, from here to here, so that is T half 1. So, this would be another T half. So, this is another T half from here to here, T half is another T half, the next T half, see this t half and the first t half which was from here to here, are not they the same, though it is not drawn to scale, but are not they the same. Again if you go for the next, so this is if I say this is t half 1, this is t half 2 essentially, okay, this t half 2 from here to here. Then if I go to t half 3, again that stretch it would be equidistant, that means they would exactly be the same. So what this plot is telling you, it is telling a lot of things. First, if I am going to plot the concentration of A as a function of time, this is what I am getting, right. A0 is 100% as starting from at time t is equal to 0 is A naught, which is 100%, right. As time goes on, how does the concentration of A decrease? It decreases exponentially as a function of time, as the exponential factor, right. Now when it comes to 50%, it would be t half. So if it is 50% it is t half, then I can say that this 50% should corresponding to my first t half, which is half of A naught, right. Now from 50%, if I take another t half, I should go to 25%, which is here, which is essentially 1/4 of A naught. So this 25%, so from 50% 25% is my second t half, and you can say this t half and this t half, they are exactly the same. Why? Because t half for a first order reaction is a constant, right. Now look at the relaxation time, which is given by this. So what does it mean? It means that the time it takes for it to decay to about 63% of its initial value, that is my relaxation time. So this is where 63.2% is, and if I read off the corresponding time from the time axis, that would be my tau, which is my relaxation time, right. Hence from this first order plot you can actually, or this exponentially decaying plot, you can read off a lot of things. So this was the end with the first order kinetics, and next class what we will do is we will start with second order. Okay, thank you.